Good morning, everyone. Welcome to the KubeCon, and specifically welcome to our talk. In today's session, we talk about how we manage our workloads using local storage, specifically in a multi-cluster environment, and using logical volumes as a way to provide isolated disk space for them. We'll talk about the design of our solution rather than how the implementation details. Before we go into the deck, let's introduce ourselves. Myself, Amar. I'm a software engineer in Microsoft. I'm working part of a platform team which manages multi-cluster Kubernetes fleets. I'm involved in this project for the last 4+ years.
And I'm Arathi. I'm a software engineer at Microsoft. I'm in the same team working with Amar. I have 4+ years of experience in working on a team building high-scale infrastructure for containerized workloads.
Quick looking at our agenda, we will introduce our multi-cluster architecture and how we do our workload orchestration in that, understand the key demands for our workloads using the local storage, and we delve into our solution where we understand how we track the capacity and do the dynamic local storage provisioning, and finally, how we do capacity-aware scheduling. And we dwell into the scenarios, how we understand various usages of this local storage, and end with our future goals and Q&A. Okay, so let me briefly introduce what is our architecture. So our Kubernetes deployment architecture is built upon multi-cluster Kubernetes fleet. In a simple terms, a fleet is a collection of workload clusters, and these workload clusters are managed by one common control plane. So that's when they form a fleet. And this control plane is another Kubernetes cluster we call as control cluster. And all these worker cluster has a representation of them in the control cluster as a namespace. So all the resources of this worker cluster have a place in the control cluster in their specific namespaces. And these worker clusters are independent, so they work independent of other worker clusters, and any other worker cluster going down will not impact any other worker cluster. And these worker clusters are interconnected. It means a pod running in worker cluster A can directly communicate with a pod in worker cluster B without going through any other external load balancers. They have the direct connectivity. And all these worker clusters communicate to the control cluster with the control cluster API server. And they kind of interact with the control cluster API server to bring the workloads that should be running in the worker cluster. And this worker cluster has no external access. It's only to the control cluster the whole fleet is accessible. And this fleet is a shared resource across many teams in Microsoft, which means it should be multi-tenant. All the workloads get submitted to the control cluster, and the control cluster orchestrates the workloads across these worker clusters. Let's understand what a worker cluster entails. A worker cluster is another Kubernetes cluster having its own control plane and its own node pools. And it can have wide variety of node pools bringing different type of capacities. A node pool could bring a GPUs, a node pool could be compute optimized, a node pool could be memory optimized, or a combination of all those. And a specific example we have shown here, there are 3 nodes in a worker cluster, each bringing different disk types, and which is pretty common with different various capacity types available outside. And with each node types, you bring different type of disks. Some have NVMEs, some have SSDs. A specific Kubernetes cluster will contribute to a fleet when there is an agent running called syncer in them. This is the glue which connects a worker cluster to the control cluster. This syncer plays a very vital role. It pulls the workloads assigned to this worker cluster from the control cluster and locally applies. Once the workloads are locally applied, the Kubernetes native control plane takes over and orchestrates the workload within the worker cluster. And syncer also does the other vital role. Basically, it syncs the state back to the control cluster. When we say state, it means a lot more details, like how many nodes are available and how much capacity is free in each node, what type of resources are available in the node, and all those. And even the states of these workloads in the cluster. And this status is constantly uploaded to the control cluster. The control plane which is the brain for the whole fleet, kind of manages the whole lifetime of this worker cluster. So it is the one which provisions and deprovisions and even kind of orchestrates the workloads into them. So we built an Uber scheduler on the similar lines of the Kubernetes scheduler. So when a workload is kind of submitted to the control cluster, the Uber scheduler, which is another controller, watches on these and acts on them. It basically filters all the possible worker clusters the workload can run, kind of sort them, and finally place. There are small nuances we have taken. When you make a decision to place, we prefer to slice the workloads. When you say slicing, what it means that a workload, suppose a deployment comes with 10 replicas, and we see the capacity available in 2 worker clusters, we prefer generally to slice it. That gives an advantage that if one worker cluster goes down, there is always another worker cluster to back it up, and the application availability is not completely down. Apart from that, since it is the shared resource, this fleet, we do support quota management. Multiple teams using the same fleet, the quota is controlled in the control cluster. The Uber schedule will do the quota management that no other team is overutilizing their quota. With that context, let's understand the demands of the workloads using local storage. The first foremost demand, the workloads needs to kind of specify their requirement for the local storage. Requirement could mean the disk type they need and the sizes they need. And the workloads should be placed in the worker cluster where there is sufficient capacity. And the capacity needs to be guaranteed in its lifetime. So while the pods are running, the capacity should not be taken away. And these workloads tend to move across the worker cluster. So there needs to be a kind of constant cleanup. And the moment the workload is deleted, you have to remove, kind of take out that local storage use so that other workloads can start using it. Another kind of scenario, what we observed with various kind of workloads coming into the fleet, they tend to use the local storage for various purposes. We'll talk more in detail about this specific usages, and which brings in the very unique scenario of wanting the local storage shared across multiple pods of that workload. With that context, let's delve into our solution.
Yeah, thanks, Amar. So we saw how the infrastructure looks like. We'll dive into the design. So before that, I would like to see a show of hands on how many of you know what CSI is or what CSI driver is? That's great. How many of you have experience building a CSI driver? Wow, okay, nice to see some hands. So for the benefit of everyone, I'd like to touch a little bit on CSI. CSI, or Container Storage Interface, is a standard for exposing storage systems to containerized workloads on container orchestration system like Kubernetes. And CSI driver, it's a plugin that allows Kubernetes to provision, attach, mount, and manage storage from a storage system in a standardized way. So it can be considered something like a middleman that is talking between the orchestration layer and the storage layer. It's a plug-and-play mechanism, meaning a CSI driver can be authored to support multiple orchestrators and multiple storage solutions. So this is about CSI, a small brief about CSI. 2 important objects will be used a lot in the upcoming slides, so I want to give context about that. The first is the persistent volume claim. This is a native Kubernetes resource. This is like a request for storage by a user. So we see a sample snippet on the right side of the slide. So what does this mean is the customer is asking for around 1 gig of storage under the storage class name standard. Now, what is a storage class? That is another native Kubernetes resource. This provides a way for administrators to describe the classes of storage that they offer. And each storage class will be mapped to a CSI driver for provisioning volumes. Let's go a little bit deeper into storage classes and what we offer as admins. So as mentioned earlier, our infrastructure has diverse machines, each with different disk configurations. So in order to optimize the resource usage and allow ease of access for our customers, we group similar types of disks into something called volume groups and expose these as storage classes to customers. So in the slide, we see 2 samples of storage classes. One is local NVMe, and the second is local SSD. So customers can choose the storage class that they want depending on their application needs. Maybe they want high performant disks, they can choose local NVMe. Maybe they want to reduce cost, they can choose local SSD or local HDD depending on the offerings. So these storage classes are mapped to the LVM CSI driver. Speaking of the LVM CSI driver, this is a CSI driver that we have authored. This is a logical volume manager based CSI driver. We drew some influence from the open EBS LVM architecture. But the reason we had to build our own CSI driver is because of our specific partner requirements that we'll talk about in the next slides. As we call it the usage types, we'll dive more into that after the implementation. So the LVM CSI driver is designed in such a way that both the controller service and the node service are clubbed together into a single container. And because of this, each node is going to have one instance of the LVM CSI driver. The CSI driver that we have built adheres to the CSI semantics, ensuring compatibility and reliability across the board. Now, bootstrapping. So we've seen what we are offering to customers. Let's talk about the setup we need to do before we provision the volumes. So each storage class maps to a single or multiple volume groups. Now, how are these volume groups created? So in the picture we see in node 1, we see 2 NVMe disks available. These disks are initialized to create physical volumes, and physical volumes of similar type are grouped together to create a volume group. So when there is a request to the LVM CSI driver under the storage class local NVMe, a corresponding logical volume will be created in the local NVMe, VG NVMe volume group. These operations, the bootstrapping operations, are done during the node startup time. Now, we saw about the setup, we saw about the offerings. Let's go on to the actual design, starting with capacity tracking. So the model is such that we have a control cluster and we have multiple worker clusters and multiple nodes inside them. So at any point in time, the control cluster must have the real-time information about the allocatable capacity, that is the remaining capacity in each of the worker cluster, in each of the nodes. So to facilitate this, we have two documents in play. The first is the CSA storage capacity. This is a native Kubernetes document under the storage.ktos.io. So this document is created by a component called external provisioner that you see inside the box in the LVM CSI driver. This is a sidecar container that runs alongside the main container in the LVM CSI driver. One of its primary role is to continuously monitor and report the allocatable capacity in that node for each storage class. So we see a sample snippet here, the CSA storage capacity. Certain fields are highlighted. What do these signify? It means that under the storage class name local SSD, there is a remaining capacity of around 2.6 TI in the node 1, that is the topology node 1. Similarly, there will be multiple CSI storage capacity documents for each pair of storage class and node, the topology. So the capacity field, so it needs to keep updating, the value needs to keep getting updated based on real-time information. External provisioner is the component that will be doing that. Periodically, it pings the main container of the LVM CSI driver, the get capacity API call, and the LVM CSI driver measures the remaining capacity in the volume group and returns the value, and that is subsequently updated in the CSI storage capacity. So we've seen how the capacity is tracked in the worker cluster. Let's move on to the control cluster. The second resource that comes to play in this capacity tracking is the fleet node custom resource. So this is a resource that we as admins maintain, and what does this signify? This kind of captures the details about each node in the worker cluster. So each node in worker cluster will have a corresponding fleet node resource in the control cluster. So it will contain details like the pods running, the selectors, the images present, capacity, etc. The main field we want to focus on is the allocatable section here. You see the highlighted part. Under allocatable, we'll have one entry for each storage class available. So we see that local SSD storage class has around 2.6 TI, which matches the information present in the CSA storage capacity. So someone needs to update this. The component that keeps the sync is called the syncer, which Amar mentioned earlier. So syncer continuously watches for the CSA storage capacity updates, and once there is an update, it quickly updates the fleet node, corresponding fleet node custom resource. This way, the information is tracked between the worker cluster and the control cluster. So this allocatable field will be used by the Uber scheduler, the component you see on the right side, for efficient and intelligent capacity-aware scheduling, which we'll see in the next slide. So We saw how tracking works. Let's see how a request flow goes like. This is how the current setup of the control cluster looks like. We have a couple of fleet nodes. We have the Uber scheduler. Now, a workload is submitted. What is a workload? A workload is basically a bundle of Kubernetes manifests. It could be a pod creator resource like deployment, daemon set, or stateful set, or job, or cron job. And certain supporting documents like service, role binding, persistent volume claim, etc. So for our example, let's take a pod creator resource, the deployment, and a persistent volume claim. So here the user is requesting for a storage of 2 TB under the storage class name local SSD. So when the workload is submitted, the Uber scheduler, whose primary work is to keep watching for workloads, creation and updation of workloads, kicks in. Now, Uber scheduler scans through all the fleet nodes present, checks for the available allocatable capacity in the corresponding storage class across all nodes, and filters the candidates from the list based on the request. It does through a greedy approach. So in this example, we see that worker cluster B has 2 nodes that satisfy the requirement of greater than 2 TB. So it's safe to send the workload to worker cluster B. The workload is further dispatched to worker cluster B. Let's see what happens in the worker cluster B. Before the workload comes in, let me talk about the current setup. So we see a volume group in node 2. The volume group, the total capacity is 6 TB. There are certain logical volumes that were created earlier for some other pods. So the current available is around 5.5 TB. Now, there is a LVM CSA driver that's running, and we see in the CSA storage capacity, the value of the allocatable capacity is reflected appropriately. Now the workload comes in. The syncer that's there in the worker cluster notices the workload and applies all the Kubernetes manifests in this workload slice. Now, the deployment was one of the manifests that we saw in the example. The deployment object gets created. The pod gets instantiated. Now, the pod will be in waiting state and kube scheduler will notice this. Now, kube scheduler needs to schedule this pod to one of the node. And kube scheduler does this by reading the CSA storage capacity documents to see which node has enough capacity as per the request of this pod. From the previous slide, we saw node 1 and node 2 had. Kube scheduler selected node 2, and the pod will now be scheduled to node 2. Now, once this is scheduled, series of events happen where the volume request will be sent to the LVM CSI driver. The LVM CSI driver will create a logical volume of the requested size, that is 2 TB. And further, this volume will be mounted at the designated path, and this volume will be now available to the pod, and the pod will be up and running. So we saw that this is a whole volume request flow. Now, our logical volume of 2 TB has been created. So the volume group current available should be updated. So now it will become 3.5 TB. Correspondingly, in the next polling interval of the get capacity API call, CSA storage capacity value also will be updated. Now the worker cluster, the capacity has been updated with the real-time value. Syncer now kicks in, and it sees that there was a value that was updated in a CSA storage capacity resource. It will go and update the corresponding fleet node resource. This way, the capacity is tracked and synced between the worker cluster and control cluster has the real-time information. Now, we spoke about volume provisioning. We spoke about capacity tracking. Volumes auditing is one important thing. We need to keep track of the volumes that were created and the requests that came in. So we have a custom resource to help us do that, and it is called the CSI volumes. We as admins maintain this. This captures the metadata for the volume request. It will include information like the pod name, namespace that requested the volume, certain logical volume details like the name, the mount path, the volume group, and other details like the storage class, usage, etc. All of the important fields are captured in the CSA volume. This is purely for audit trail for volume lifecycle management. Now let's talk about the lifecycle of a single volume. So we don't want volumes, the logical volumes, to be sitting idle when the pod goes away. So we suggest partners, our customers, to use generic ephemeral volumes. So these exist only for the lifetime of a pod, and this is defined something like this in the volumes section, ephemeral.volume claim template. So Kubernetes automatically provisions and deletes the associated PVC when the pod is created and deleted. So we saw how the volume provisioning works. I'll hand over to Amar, who will further be talking about the local storage usage.
Yeah. So the fleet is hosting is multiple workloads from different teams. So it's a multi-tenant system. And when we looked at the workloads using the local storage, we observed the usage having of different patterns. I mean, the specific reasons why they use the local storage. And we broadly classified into three possible usages. One, we call it a scratch. Basically, the storage is needed only during the lifetime of the pod. Once the pod gets deleted, the data what is present in the local storage has no significance. It can be immediately wiped out. So those kind of usages, the ones can easily clean it up once the pod moves away. And another common scenario what we saw for using the local storage is for the configuration. So when you say configuration could mean your settings for your pod kind of to enable, disable some features in your workload, or it could be some kind of a ML model that your pod is using to kind of run, serve your traffic, right? So a specific requirement comes with the configuration. They tend to use the same configuration across the pods of the workload. So in those scenarios, we kind of want to kind of share the same local storage across multiple pods with running the same node for the workload. And this gives the consistent configuration access to all the pods for the workload. And third, very peculiar and not so common, is the logs. Traditionally, logs go to an external storage where they're processed, indexed, and used for investigations. But at times, what we observe, there are some kind of verbose and debugs logs which are needed for a shorter duration. And these logs are humongous in nature, and we don't want to kind of store them in external storages to avoid the cost. So the local storage is a cheaper one to keep these logs for a shorter duration. So, but what it brings the challenges is that the pod can move out of this node, but the logs still are needed to be retained for some more time. So what we do is that unless there is enough disk capacity, we try to retain those logs and try to regularly clean up the logs, ensuring that there is a sufficient disk space always available. These kind of usages, what we saw across the workloads, we built our own CSI driver supporting these scenarios. Let's look at the telemetry. We're capturing the top four metrics, what we closely look at. The LVM CSI driver does a lot of actions while provisioning the volumes. So we track the number of requests each LVM CSI is doing and what kind of requests it is doing and how common these requests have been happening. The common requests like provisioning an LVM, formatting the LVM, deprovisioning the LVM, the mounting the LVM. So we track the number of requests each LVM CSI driver instance does. And these operations are not short time in nature, so they tend to take longer time. So we curiously want to observe the latency, how much each operation takes. So that's our next metric, the request latency seconds, which kind of measures how much each operation takes. And the third metric, it is more not from the platform and more from the customer, the logical volume available bytes. It's a metric we constantly emit, which says that this pod has asked for a logical volume, it has been provisioned, and how much is the current usage of it. So this helps in managing the required local storage space and helps later to plan effectively either to reduce the requirement or increase the requirement. And the last one, the request volume size bytes, is a metric we track as a platform to understand the common requirements of the volume sizes so that we prepare our capacity in such way. With that, we'll go to feature goals. Today, we provided a kind of isolation to the pods by creating a logical volumes within each node. That solves half the problem. One, the scheduler today uses the CSS storage capacity to kind of filter the nodes but not score the nodes. So this is the Kubernetes scheduler doesn't do that natively today. So we are planning to extend the scheduler by building an extension to it so that it effectively scores the nodes so that the nodes which have more capacity are utilized first. And with LVMs, we give the guarantees on the space, but IOPS, there is still not a solution yet. And IOPS is really important too because a noisy workload sharing the same shared disk can actually impact other workloads. And last, it's very important, we want to make this available soon on the open source. With that, we are open up for the Q&A. So question is, how is it different from the Topo LVM, right? Yeah, so Open EBS LVM, Topo LVM, very similar principles to create the LVMs. And how we track, I think Topo LVM doesn't use CSS storage capacity for tracking. They have their own schedule extension to do that. And we use CSS storage capacity, and that's what even Open EBS does. Very similar principles, because the way we track we want to share the volumes across the pods. That's not done by these native components. Sorry? OpenShift, I'm not aware, sorry.
Hi. Yeah. Hi. Yeah, that was a great session. Thanks. I just wanted to ask a couple of things. One is the LVME CSI driver. Is it being enabled as a plugin, or is it present by default on all your worker node clusters?
It's a daemon set running on all our workload clusters.
Okay, if that's the case, like given that you have some kind of operator running in your control plane, right? You showed that CR. So I understand that you mentioned that it is going to, the scheduler will check where the resource is available and will go and schedule there. Wouldn't it be a better approach if it's more like, I want the CSI driver on this worker node cluster, create the CR, and the CSI driver will come up there? And then is there an option where we can actually specify this is where I want the workload to go, rather than more like a labels concept in Kubernetes?
Okay, so the question is that can the workload decide which workload cluster
Exactly.
to go? Right.
You can
Actually, no. Our design, we don't want to expose our worker clusters to the workloads. And the reason is that our worker clusters are ephemeral in nature. They tend to go out. And the way we use, that gives us the flexibility kind of remove a workload from cluster on the fleet and bring up a new one. And we never want to kind of expose our workload clusters out.
All right. Just last question. I didn't take a good look at your storage class, but do you support both file and block storage?
Currently file, but block storage I think we want to do.
All right. Thank you.
Thank you for the session. Hi. My name is Hello. My name is Guru. Just wanted one question. See, what kind of QoS applications do you support? Because this is for best effort apps, or suppose if I have, you have a Uber scheduler that sprays the job, that partitions the workload and places into different things, right? Suppose, and you also spoke about availability. So that means it is possible that the same workload can spread across two availability zones.
Yeah.
So in that case, imagine that I have a stateful set which is feeding into some deep learning models on top of it, which is consuming from that. So would I not get disparate quality of service for a specific worker, for specific pod in a deployment which is placed on this availability zone versus the other? How do you handle those kinds of things if you have an architecture?
Okay, so the question is that how do we handle the disparities of the worker clusters, right?
No, the quality of, because within the same deployment, so if I have 10 replicas, right? So in your architecture, 6 replicas can be on one availability zone, 4 can be on the other. So there will be chit chat, right? Suppose if they are massively parallel applications, they have to speak between themselves, and storage is the means for me to do it, right? So in that case, some things will be reading and writing from the same persistent volumes. So in that case, when you are designing itself to spread these across different availability zone, I would not get the same quality of service for all these replicas in my deployment, right?
Correct. So because you're saying there is no control on the IOPS.
Exactly.
Yes. So IOPS is surely the thing we wanted to work on, so that when we place a workload on a node, we can't kind of give the guarantees on the IOPS as well on the disk, so that they have the same behavior across the clusters.
So this is still for best effort quality of service only.
Yes.
Hey, hi. Just a small question. Did you make any exploration of different layouts onto this persistent volume? Let's say if you have a stripe mirror, or probably in that case, you're actually using a mirroring. Or probably in this case, if I have to use this solution, an on-prem solution, I have an attached storage where we have a multiple storages, concurrently writing to a single storage pack over there. So any exploration on the IOPS and the performance you have ever made, especially with the workloads on this?
You mean to say when compared to the network storage?
No,
Is it-
simple. Like whether if you have a persistent volume, and I'm going to implement different layouts into this thing. It's a stripe mirror, or maybe in this case, it's just a mirror, right? I probably can also have a rate configuration of this thing. And then if you inject the workload out of it, how's the IOPS going to be? How's the performance going to be with that there in that case, right?
Yeah, so most of the workloads don't kind of need that kind of a RAID kind of a layouts. They kind of use it for the mostly for the cache preservation while the workloads are running. And even if you wanted for longer usage, then to kind of push the data to the remote storages for later consumption.
Okay, because I prefer like if you have different redundancy within the block devices down there, which you can actually write it within the YML files, you should see some of the performance, right? If you have a simple block device, or if you have a stripe mirroring or the mirroring in that case, then you actually start working at redundancy apart. So something I was thinking of, if you can
Yeah, so
actually
we don't have
explore
mirroring support today, yeah.
that today.
Yeah.
Thank you very much. Appreciate it.
Sure. Actually, I was having a doubt. If here,
Oh, yeah.
does the control plane have the capacity of isolating the worker clusters? Like I want some ports to not to communicate with some of the ports into the worker cluster. Do we have that isolation provided in the control plane so that worker can be accordingly like the workloads in the different worker clusters?
Okay. Can we support network policy at a fleet level? Is that the question, right?
Yeah.
Yeah, so it's a good question. I think today in our setup, each pod across the fleet can talk to other pod. We don't have the network policy at the fleet level, but at an individual worker cluster level, they can have a network policy.
Okay. Thank you.
Hello. So you mentioned that this is based on OpenEBS, or at least like the foundation is on OpenEBS, right? So, and you also mentioned that you plan to open source it at some time.
Yeah.
So, do you want to contribute back to OpenEBS instead of open sourcing this as a separate project?
Sure. Sure. I mean, we would like to contribute back. OpenEBS still works for Linux. We have our workload feature having in Windows as well. So we would add even the Windows support to come in, and we contribute back there.
Thank you.
Hey, very nice talk. Thank you so much. So the way my mental model of this is that you have a default Kubernetes scheduler. It schedules based on CPU memory constraints. You added the storage constraint. I mean, I think that's the summary of this. So the question I have is that the kind of applications that need this, you shared, they use it for local cache. Like how big of a storage requirement typically you see from the applications, like your workloads over here? That was one part of the question. Second, this scheduling really depends a lot on like how often you sync from your worker clusters to your main cluster, and so it really depends on how well synchronized that is. Otherwise, things can really screw up. So, can you comment on these 2 points?
Sure. The first question on the capacity requirements, we have seen ranging it from few MBs and 2 terabytes. That's what we have observed. So a max of 5 terabytes we have seen, one single pod was requesting for in the local storage. And on the other question of the synchronization, there can be delays in synchronization, but the Uber scheduler kind of is smart enough to say that if the synchronization is not happening, it will kind of place the workloads to another Uber workload cluster, assuming the work cluster is maybe not performant.
And so on the first one, the case where you require high storage volumes, that's those are typically ML model cases. Like, I mean, I'm just wondering what are the kinds of scenarios where
they're not ML models. There are other use cases also we have observed. Even I said there are too much voluminous logs. Some components emit out, which are needed for a shorter duration of the time.
Got it. Thank you.
Okay, thanks everyone. We will be available if you have any other Q&A. Thank you.
Yeah, thank you.